Mhm.
So welcome everyone to our next researcher training, how to get the most out of your collaboration with a biostatistician. I'm very pleased to introduce Dr. John Rice, who devotes part of his time to helping CWHR researchers. So Dr. John Rice is currently a research assistant professor in the Department of Biostatistics and Informatics and a biostatistician with the Adult and Child Consortium for Health Outcomes Research and Delivery Science, or ACCORDS. He received his PhD in biostatistics in 2015 from the University of Michigan, followed by a postdoc at the University of Rochester. Dr. Rice has been working with CWHR researchers for nearly 2 years. His methodological research is focused on missing and coarsened outcomes, longitudinal and correlated data analysis, and recurrent events. Areas of application include cancer survival, HIV screening, vaccine uptake, and other health outcomes. And Dr. Rice did send me his slides, so you're okay with us sharing those after the talk, correct?
Yes.
So we'll send those out along with the evaluation after the presentation today.
Great.
And with that, I'll send it over to you.
Okay, thanks, Anne. Is it okay for me to share my screen now?
Yep.
Okay. Okay, hopefully everybody can see. So, hi everyone. I am, John Rice. As Anne said, I'm a biostatistician with ACCORDS, also in the Department of Biostatistics here at the University of Colorado. And I do have part of my time to help you guys out, so with the center. So today we're just going to talk about a few aspects of biostatistical collaborations that hopefully will be helpful for you as you work with me and or other biostatisticians around campus. So, we have a few objectives as kind of biostatisticians, collaborative biostatisticians on campus. And these are listed here, and we don't have to go through these in detail, but basically the goal that we have is to help you with quantitative research or quantitative methods for your research, including the development of new or innovative methods, because many times it transpires that the research that you're working on might not fit into a existing statistical method. So there's times when we need to kind of become creative and either apply methods in new ways or develop new methods kind of from the ground up. And another aspect of this is applying the appropriate statistical methods, because there are many times when in collaborations in the past where I've been interacting with various researchers where it's not necessarily obvious to non-statisticians which methods are appropriate or not. So that's another thing that we help with is explaining when and how certain methods apply. And finally, one of our objectives is to help train researchers such as yourselves in kind of quantitative methods and collaborative relationships with biostatisticians. So today, just the outline of the seminar today. First, we'll talk about kind of the basics of collaboration between a statistician or a data analyst and a researcher, a clinical researcher such as yourselves. And then we'll talk a bit about power and sample size, since that's a good deal. I would say probably the majority of what I help with in general with the center is power and sample size for grants. So we'll talk a bit about that because there's various aspects of that I think it's important to be aware of as a researcher. And we'll get into that in more detail. And then finally, we'll talk a bit about some data analysis. And we might run out of time there. I think we may have done that in the previous incarnation of this training. But as Anne said, we'll share the slides. And of course, you're free to reach out and email me and we can meet and talk through stuff if we don't get to it. So my role for, yes.
Sorry to interrupt. If people have questions throughout the presentation, would you like them to raise their hand, put it in the chat? Or wait until the end?
Thanks, Anne. If you wouldn't mind monitoring the chat, and just if you could just like pipe up and let me know, and then I can address it, because you're right, it's kind of hard to see the when I'm sharing the screen, it's hard to see people. So
okay.
So yeah, if you could monitor, that'd be great. Thank you. Right. So as a biostatistician working with the center, I'm primarily kind of tasked with helping with study design, which includes power and sample size calculations, and also with manuscript preparation. So this is kind of a catch-all phrase there, because manuscript preparation can mean a lot of things, and there's times when I've been asked about there's an existing manuscript that's come back for revisions, and I've been asked to kind of consult on responding to statistical critiques. So that's one aspect. Also, I can kind of help earlier on in terms of writing up the manuscript, writing up the methods, whether or not I helped with the planning of the study. So that's kind of a pretty broad area. And data analysis is often a part of this, but it's not my primary responsibility. The main reason I'm doing data analysis for you as researchers would be to help with power calculations primarily. And again, in terms of the manuscript preparation, there may be some data analysis I can help with, but in general, that might have occurred already. So one of the things we're going to talk about today is the distinction between data analysts and biostatisticians. And in your grants, you're often or usually going to need to budget separately for both. The biostatistician would typically take a smaller percentage than the analyst, and the analyst would be the one who's actually running the code, the statistical or data and analytic code to do the analysis, whereas the statistician is kind of responsible for supervising and overseeing that process. So again, I'm perfectly happy to do some data analysis for you guys if it's to help with a manuscript or power and sample size for a new grant. But unfortunately, I don't have the time to do data cleaning or anything like that. So a key point here is just that when you're planning a study, you need to budget for a biostatistician and a data analyst or data manager, and those are different, kind of slightly different positions as well. So the basics of collaborations. So one of the key things that I'm responsible for in a collaboration is to help you translate your clinical question into statistical terms. And that includes kind of formulating a model and identifying the methods by which we can estimate parameters in that model, and so on and so forth. So there's a lot that goes into that, and that's where we get into the kind of the back and forth, where your clinical knowledge will inform what I think and how I operate in terms of the statistical side of the research. Another aspect of that, so I mentioned model building, but also it's important to identify kind of what data to collect and how to collect it to answer that question, because you could collect a ton of data, and without kind of consultation with a statistician, it might not actually be that helpful to answering your question. So this is another kind of plug for involving a statistician early on in your research. And that's not to say that you can't contact me later. Of course, some of you're new, some of you are new, or some of you have been working with another statistician, and I'm happy to help at any stage. It's just, again, it's a good thing to be able to involve the statistician early on to avoid problems with the data and or methods later. And then finally, aiding in the analysis of the data. And like I said, I'm capable of doing analysis, but it'll often be that I would kind of oversee a dedicated data analyst. and kind of provide sort of just input on the methods to use and just the general kind of analysis plan to answer your research question. So any kind of collaboration is going to be fraught at the beginning with gaps in knowledge and miscommunication. Because as statisticians, we understand analysis and statistics, but you guys know the clinical context and the scientific background for the area that you're working in. And you know, we typically, some statisticians are more specialized than others, but for example, I work with people in many different areas of application, including sleep research and cardiovascular research, you know, vaccine studies. So it's our knowledge of these subject areas is necessarily a little bit less deep than, you know, might be ideal. So it's important for you guys to kind of educate us as we're going along on the content area. And you know, speaking for myself, I'm always very excited to learn about, you know, these things, because it's just very interesting to me, you know, the different areas of application that people work on, and then kind of, you know, as I said, part of my role is to figure out what statistical methods would apply and would help you answer your questions. So I think that's kind of a fun aspect of what I do. And, you know, as this collaboration goes on, again, you kind of iterate back and forth, and you come to the point where the understanding, these gaps in understanding or knowledge are less prominent. And that's kind of the sign of a successful collaboration, where there's this back and forth in an exchange of knowledge between the statistician and the clinical researcher. So some logistical points, and these are things that probably nobody likes to have to think about, but that are important. You know, how often meetings occur. Again, this could vary a lot depending on the stage of the project you're at, and it could vary over time as well. Preferred format of results, and this is a little bit more in line with the data analysis. But this can be things like tables versus figures, you know, what kind of tables, or, you know, it can get very in the weeds. But it's important to, you know, let us know kind of at some point, you know, how you guys would like the results, because there's been situations that I've had where because of these knowledge gaps I was just talking about, I have produced results that were not really in line with what the researchers were looking for. So again, it's good to talk about these things early on, so it's understood, you know, what's expected of the collaboration. And one thing that can really help with that is shell tables. So, you know, you guys could create basically an empty table with column headings and row headings, and that helps us then kind of think through what we need to do to get you the results that you need. Deadlines are important to be kind of upfront about as well, because, you know, we do work on a lot of different projects, so kind of juggling the priorities is important. So again, we don't drop the ball on anybody's research. Level of detail, that's another one that's kind of goes along with the format of results. And that can include things like breaking down summary statistics by subgroups or something like that. And again, that's important to go through, because, you know, we don't want to end up in situations where we give you way more than you need, and then that's, you know, a lot of time we spent on something that we maybe could have been a little bit more efficient about, or alternatively, we don't want to, you know, kind of miss out on important detail that you need. So this is another good thing to go over. And then authorship. Again, this is I think always a tricky subject, but I think the earlier it's discussed, the better. And from my perspective, you know, if I would expect to be included as an author if I give, you know, substantial input on a manuscript or study design or something like that. But of course, it's a discussion. You know, it's a discussion between us and the co-authors, and you know, we figure that out. But it's good to do that early on. So moving into sample size and power, which is key for designing any study. So determining the correct sample size is going to depend on a lot of things. It's going to depend on the study design. It's going to depend on the analysis plan, which means, are we doing a regression? Are we doing a t-test? What are we doing? And then, of course, it'll depend on the outcome in various ways. Is it a binary outcome? Is it continuous? Et cetera. And there's kind of two potential problems with sample size, right? So if the study is, quote, underpowered, you might have non-significant results simply because your sample size was too small to detect the difference that you needed to find. But it could also be because the treatment doesn't work. And in this situation, you end up with a study that almost is I don't want to say a waste of time, because there's almost always value in data that's collected, but its primary purpose has not been achieved because at the design stage, it wasn't properly sample size wasn't properly calculated. On the other hand, if you're overpowered, then you have a study that's larger than required, to answer your question of interest, and that could be a waste of resources. Additionally, it could be that you find statistical significance that doesn't correspond to a clinically meaningful difference. And this is something you guys have probably encountered, the distinction between statistical and clinical significance. But I think that's a good point to reiterate. And statistical significance will be achieved in a large enough sample for any non-null effect. So as long as your regression, as long as your beta is different from 0, even if it's 0.001, if you have a large enough sample, you're going to find statistical significance. And when I say the true value, I mean like the population value. But it depends on your context if that's meaningful. And in some contexts, a beta of 0.001 could be meaningful. And that has to do with things like, the scaling of the variables involved. But I think it's really crucial to remember that, despite the finding of statistical significance, that may or may not translate into, a clinically meaningful effect. So when we do calculations for sample size and power, we're making assumptions. We're making a certain set of assumptions that are needed because these power calculations take a certain set of inputs or parameters. So a couple things to consider that we need to understand between you guys and myself is what kind of difference do you expect between the groups, and this is kind of in the context of a two-arm study. So what kind of difference do you expect between the groups? And that could be a difference in means of an outcome, or it could be a difference in proportions, or you could have more, kind of exotic things like a difference in survival probabilities and things like that. Another key point is how much variability do we expect in the measurements? And this is kind of measured by the standard deviation of the outcome. So how much spread is there about the center of the distribution of the outcome? And we'll look at some examples of this in a moment. And then, as I said, what is a clinically relevant difference? Because, and this is a distinct question from what difference do you expect, because if you expect a difference between the groups that's not clinically relevant, then that's kind of another discussion. But, it's important to kind of, again, go back and forth between these to make sure that we understand, that we're coming up with a study that makes sense to do. And this is something that if you provide preliminary data or literature to in the area, it's one of the things I do is come up with estimates of these, but I can't do it without some sort of either, again, preliminary data or relevant articles from the literature. But I would say that never despair about this, because you can almost always work backwards from either stuff that's published or some data that you have to some helpful estimates. Because kind of my opinion is that some data is almost always better than no data. And this is the caveat here, is that there certainly is bad data, but from published articles and data that you've collected, there's very often ways to come up with these estimates of parameters that go into the power calculations. So I mentioned study design before, and here are a few examples of different study designs. Kind of the standard default gold standard really is the randomized controlled trial, where you are randomizing to typically two groups, so that you're controlling for confounding at the design stage. Because the idea is that when you randomize people to two groups, they're going to be balanced. These two groups are going to be balanced with respect to any factors that could contribute to their response to a treatment, for example. So that's kind of the ideal, but that's not always possible, and then that's why we get into pragmatic research, which is a lot of what we do at Accords, pragmatic trials. So this can include cluster randomized trials, which kind of further includes the subset of stepped wedge designs, if anybody's familiar with that. And then there are equivalence or non-inferiority trials. So that's, for example, if you have a situation of a drug that is, say drug A is the standard, but you have drug B that is maybe has a better side effect profile than drug A. You wouldn't want to necessarily demonstrate that it was better than drug A with respect to your outcome, but you wouldn't want it to be worse, to have it be a suitable substitute. So that's when something like an equivalence or non-inferiority trial would be relevant. And these often require a larger sample size than for a traditional or superiority design. So it's a little bit less common, but it can be something to think about, again, if you're in a context of, I think I can't remember what the term is. It's like not de-escalation, but de something. There's research that goes on campus where people are kind of trying to sort of reduce the invasiveness of a set of treatments or something, and that would be maybe a good context for these kinds of trials. Non-randomized interventions, which again, we're kind of going down this hierarchy here of other than the equivalence or non-inferiority, this kind of hierarchy from sort of most scientifically valid to most pragmatic at the bottom here. So non-randomized interventions are situations where, for practical reasons, you can't randomize, between two groups, but you still want to implement a treatment or an intervention. And again, this can require some different methods than the typical RCT. And that's the thing about all these. All these designs require slightly different methods for analysis and possibly for sample size and power. Although with sample size and power, many times we make these, as I said earlier, we make these assumptions, and some of those are simplifying assumptions that might kind of gloss over some of these finer points. But then this is a kind of the art of grant writing is balancing the sophistication of the power calculation with the sophistication of the analysis that's ultimately planned. And I always like to err on the side of a more sophisticated analysis, because you want to demonstrate in the grant that you've thought through all the possible issues that could arise for your study. And then finally, there's the observational study, which is, you haven't implemented an intervention, you just want to study differences between two groups, for example. And this is where things like causal inference kind of come up. Propensity score methods, if anybody's familiar with that. So, when you have these non-randomized studies, you often want to control or adjust for confounding factors, and that can result in larger sample size. But this is not something that's super precise, and that's something I should probably emphasize anyways, is that sample size calculations are always guesses, and they can be better or worse guesses, but they're always going to be a guess. So there's just certain things that we're not going to be able to know. So a common thing that we do is to deal with things like this is to just inflate the sample size that we've calculated by 20% or 40% or something like that, to allow for example, for adjustment for confounding factors. Because doing a really precise sample size calculation to address this would require so much more information than we're going to have. It would require information on the specific confounding factors, how many of them there are, what their distributions are. It just requires a lot more information than anybody's going to have at the design stage typically. So kind of the distinction between primary outcomes and secondary outcomes is that the primary outcome is the one you do the sample size calculation for. And then, if there are secondary outcomes that are important, you just kind of want to be sure that the sample size is adequate. And then some secondary analyses, like subgroup analyses, are just things that people kind of understand that you're probably not going to have great power for, just because, if you have good power for your primary outcome, your primary comparison between two groups, when you start to get into subgroups, you're cutting your sample size in half or even more potentially to look at these things. So it's unlikely that the same analysis would have sufficient power in those kinds of cases. But I think that's something that's often understood by grant reviewers to be a trade-off that is necessary to get the research done. But there are also cases where it's subgroups are kind of important enough that you do need to have a larger total sample size to make sure that you have power for those comparisons as well. So this last point is kind of what I mentioned about inflating the sample size. And this can be kind of fuzzy as I mentioned, 20% to adjust for confounding, or it can be something more kind of precise like an attrition situation. So if you expect to lose 30% of your sample to attrition, then you need to inflate your sample size by 43%. So 1 divided by 1 minus 0.3 to allow for that loss. So that's a little bit more precise. And, it's another point that's good to make is that reviewers often pick up on if you don't do this, if you don't account for attrition or losses to follow-up, et cetera. So this is a good thing to account for, especially in kind of a longitudinal setting. So hypothesis testing, and some of you may be familiar with this, but here it's a review in any case. So the typical form of a hypothesis for a two-group comparison with respect to an outcome is going to take the form of the null hypothesis being no difference in means or proportions or there's some parameter that you're positing no difference between under the null. And then the alternative hypothesis would be that the difference is not zero, so that there's some difference between these two groups, again, on proportions or means or other parameters. So the significance level of the test, or alpha, is the probability of rejecting a true null hypothesis. And that's going to be typically going to be 0.05. So this is your type 1 error rate, if you've heard that term. So there's a lot of terms for these various things. And then power is kind of the other side of this coin, which is the probability of rejecting the null hypothesis when the alternative is true. In other words, this is the probability of concluding that there is a difference statistically when there is actually a difference in the underlying population. So it's the probability of correctly rejecting the null hypothesis. And usually this is set to 0.8 or 0.9. So you want to have an 80 to 90% chance of correctly rejecting your null hypothesis when the null hypothesis is in fact false. And an important point here is that to calculate power, you need to know, you can't just say null alternative, you have to know what the specific alternative is. Because as you move further away from the null, power increases, as you would expect. Because for a larger difference, you would think that you would have a better chance of detecting it, kind of fixing everything else, fixing sample size, et cetera. And we'll talk a bit more, but there's flip sides of that coin as well, because larger sample size given a fixed difference is going to improve your power as well. And then the p-value is the probability of observing results as extreme or more extreme under the null. And p-values are kind of I think a little bit maligned at the moment, and there's a lot of debate about their value. For various reasons that we won't get into today, but they still are, I think, at least a good summary of kind of the level of significance of your findings. And this is why I think it's important to the 0.05 threshold, I think, is not ideal. I think you really need to look at the whole context of your results and look at confidence intervals and things like that. But again, I think the p-value is at times a good summary of the evidence. So sampling variability is an important feature of power calculations. And what it does is it reflects the random variation between samples. So there's random variation within the samples, and that's going to be kind of, each measurement that you take is a random variable. But then there's randomness also between samples. So for example, consider birth weights from 1,000 consecutive infants delivered at a city hospital. Here the mean is 112 and the standard deviation is 20.6. So if we were to draw 5 random samples of size 10 in this population, then we would end up with 5 different values for X bar, which is the sample mean, and S, which is the sample standard deviation. So the first type of variability I was talking about is the variability within a sample. So that's these, within a column here. There's randomness, between individual infants. But there's also randomness in the sample mean. So this is your estimate of the population mean. As you can see, it varies quite a bit around, the true value. And in this case, you would kind of, in large enough samples of samples, so if you were to take 50 samples of size 10, you would start to get closer to a centering around the mean of 112. But here we only see one value that's less, or 2 values that are less than 112 actually, but we see a couple that are larger than 112. So this is, there's randomness in your estimates are random variables as well, is the point here. And that's actually what we base our statistical inference on, is kind of the distributions of these random variables that are the estimated means, regression parameters, etc. So this first picture is the actual data distribution. So this is the birth weights, and this is a histogram. So this is kind of the percentage of birth weights, or percentage of samples with birth weights equal to the indicated value here. So this is the whole kind of population. And then this is the distribution of the sample mean when n equals 10. So this is, we saw 5 sample means on the previous slide. So this is looking at quite a few more means. And you can see that it's centered around 112. But it's a narrower distribution than what you see above, because what you're doing by taking a sample of more than one individual is you're reducing sampling variability, which is measured by the standard error. And as your sample gets larger, so when you go to n equals 30, you see even more of a concentration about the true value. So the lesson here is that as your sample size increases, you're getting better and better estimates of your population parameters. You're kind of closing in on the true values because you're reducing sampling variability. So as I mentioned before, there are many quantities that affect power, including the study design, the data distribution, and again, this could be binary or continuous, or it could be a count outcome, which comes up in the context of things like rates of events. It could be a survival outcome, which is time to an event. There's almost no limit to the types of outcome data distributions you could work with. Although typically it's often going to be binary or continuous, and when it's continuous, we typically assume that it's normally distributed. So another aspect of power calculations that we don't really see too much kind of fiddling with is the distinction between a two-sided test, which is what we almost always do, or a one-sided test. And the one-sided test does come up in some contexts, but traditionally and conventionally, you'll be working with two-sided tests. And what the distinction here is that the one-sided test kind of presumes a priori what direction the effect is going to be. So you can gain more power using that, but it's kind of frowned on in general contexts because it's seen, I guess, as stacking the deck in your favor at the outset. So the two-sided test is much more frequent in general. And then we talked about alpha, or the type 1 error rate, on the previous slide, which is the probability of rejecting the true null hypothesis. And the effect size, which is the difference to be detected. So this would be, for example, a difference in means, or it could be a difference in proportions. The variability of the data, and this kind of goes along with the distribution of the data. So like I said before, that's kind of measured by the standard deviation of the outcome. And this is an important aspect of sample size calculations to get to translate to an effect size that's kind of interpretable. But if we don't know the standard deviation, we can get around that using a certain type of calculation, basically. And then sample size, of course, is kind of a key as well, because as you have a larger sample, your power is going to improve, everything else being fixed. So a little 2x2 table here, showing, what kind of situations you can wind up with in this binary testing. Hypothesis testing is this kind of binary result. You say significant difference or no significant difference, and we either reject the null hypothesis or we fail to reject the null hypothesis. And one thing that you might hear is kind of people saying they accept the null hypothesis. You don't accept it, you fail to reject it. And that's just kind of, it's a little bit of a semantic point, but it's also the distinction between a superiority and a non-inferiority or equivalence test. Because that's kind of the equivalence test is sort of a flipping of, the roles of the null and the alternative. These two cells on the diagonal are kind of where you want to be, especially, up here where there actually is a treatment difference. And there's a smiley face there for that reason. But there's also a smiley face down here because that's still a correct conclusion, right? So on the diagonal, we have these correct conclusions. And on the off diagonal, we have the two types of errors. So the type 1 error, or a false positive, is when we conclude that there is a treatment difference when in fact there is not. And then a type 2 error, or a false negative, is when there really is a treatment difference, but because of inadequate sample size or other reasons, you fail to reject the null. So that's kind of the set of possible outcomes for these trials, or for any kind of hypothesis test. And then the values of beta, which is the probability of a type 2 error, and then alpha, which is probability of a type 1 error. So things that you can do to increase power, things that cause power to increase, not necessarily that you could do, but if you allow your type 1 error rate, or your alpha, to increase, then you will get a lower type 2 error rate. And this is something that we typically don't really do too much to change alpha. It's almost always set to be 0.05. But in certain situations, you might have it be 0.01 for maybe a very large study, or it could be 0.1 for like a pilot study where you're just trying to find some suggestion of an effect. So those are just some situations where you might deviate from the standard 0.05 value for alpha. Power also increases when the effect size increases. So that's the difference between the null and the alternative. And whenever I'm saying this difference, it's really a difference in parameter values. So for example, the mean is a parameter, and the mean value could vary between two groups. So as that difference in means increases, the effect size increases, and therefore so does power. As finally kind of the sampling variability piece, right? As your standard error of your estimate decreases, power will increase. And two things go into this actually. So sample size is one component of standard error, but the other component is kind of the variability of the outcome. So if we think about the sample mean, the variance of the sample mean is going to be equal to the variance in the population divided by n, which is your sample size. So in the denominator, if you increase your sample size, you decrease this standard error. or in the numerator, if you decrease your outcome variability, you will also kind of increase your power through decreasing your standard error. So this last point is kind of, a bit more about, the sampling variability of your study. So example, weight loss after pregnancy. So we have two treatment groups, and our primary outcome is whether an individual loses at least 5% of their initial body weight. So this is a binary outcome. And that's a little bit tricky because, we have this 5% threshold. So, weight loss itself is continuous, but this is kind of a thresholding of that. So this is yes or no, does somebody lose at least 5% of their initial weight? Because this is a binary outcome, we think, we think through this and we understand that the appropriate analysis would be a two sample difference in proportions, because that's the appropriate test when you have a binary outcome, because the parameters that you're estimating are proportions. So within each group, you're going to estimate the probability of losing at least 5% of initial body weight. And you're hoping, I assume, that you have a higher probability of this event in the treatment group versus control. So if we set alpha equal to 0.05 and power equal to 0.8, then we can go through some calculations depending on different expected differences. So in this case, with the difference in proportions, it's going to depend on whether we're looking for 30% versus 50% or 40% versus 60%. And you might say, well, hold on, this is the same size of a difference. It's 20 percentage point difference in either case. And so it seems like you should get the same sample size either way. But because this is a binary outcome, the variability or the sampling variability actually depends on the probabilities or the parameters that you're comparing. And that's not the case for a continuous outcome that's assumed to be normally distributed. So this is kind of a key difference in power calculations for binary versus continuous outcomes. Excuse me. So carrying through the calculations, if we're looking to detect a difference between 30% and 50%, then we would need 93 patients per group. Whereas 40 versus 60, we'd need 97 patients per group. So there's not a huge difference here, but there is a difference. And that difference becomes more pronounced the further you get to the edges of the probability scale. So the closer you get to 0 and the closer you get to 1, you'll see more of a difference. And the reason for this is the variability of a binomial variable is kind of maximized at a probability of 0.5 or 50%. And it becomes less as you move towards either a probability of 0 or a probability of 1. And this can be advantageous in some studies where you have a very low prevalence or probability of the outcome, because then you often need fewer subjects in your study to detect a difference. So this is kind of just a peculiarity of binary outcomes and power calculations for differences in proportions. So another way to look at this data would be to have weight loss continuous. And this would be, assuming, well, you don't have to assume that weight loss is normal, but if your sample size is large enough, even if it's not a normally distributed outcome, you can apply the two-sample t-test. And this would be the same thing, for example, as running a regression model, a linear regression model with weight loss as the outcome, and then a variable in the model for treatment group. So your beta for the treatment group variable would equal the difference in means between these two groups. If your treatment group is binary, right? 0 or 1 for control or treatment or intervention. So if we, we consider this as a secondary outcome, and then we fix the sample size per group at 93, which is what we found we needed for 80% power for the primary outcome, which was just yes or no, 5% loss. Then we can solve for the minimum detectable difference in mean weight loss. And this is a term that I think is maybe less familiar, but it's common in kind of discussions of power and sample size, because this is one of the cases where you fix you fix all the other inputs to the power equations, and you solve for the effect size, essentially. And what we find is that this is 0.41 for 80% power, or 0.48 at 90% power. So this effect size is measured in units of standard deviations of the outcome. So we refer to this as Cohen's d. So this is what I mentioned earlier, that even if you don't have information on your the variability of your outcome, you can still carry out your power calculations using this concept of Cohen's d. And Cohen's d is a very commonly used measure of effect sizes, and there's rules of thumb about sizes of effect. I think 0.2 is considered small, 0.5 is considered moderate, and 0.7 is considered large. Although those are pretty subjective, but they're often kind of accepted as by reviewers. For example, if you were looking for an effect size in terms of Cohen's d of larger than 1, then that would be considered a very large effect, and that might be looked at as evidence of an underpowered study, unless you have good reason to believe that the effect size will be that large. So it's always kind of a negotiation between what's plausible from in terms of how your intervention could move the needle versus what's feasible in terms of how many people you can get. So Cohen's d, again, is useful when you don't know the outcome standard deviation, but if you do know the outcome standard deviation, you can translate back and forth between them. So if the standard deviation of the weight loss outcome variable is 10, then we could detect a difference between groups of 4.1 pounds or 4.8 pounds at 80% and 90% power respectively. So all you have to do is multiply the standard deviation of your outcome by the Cohen's d to get the effect size in units of your outcome. So another design that kind of you might see from time to time is a matched pair design. And this is preferred often because it is more efficient than a two-sample test, because you're making comparisons within people, and there's or within units. It doesn't necessarily have to be people, because again, a matched pair could be 2 observation times for one person, or it could be 2 people who have been selected to be similar to each other. There's a lot of ways that this can arise, but I think one of the most frequent ones is kind of a pre-post design, where you take the measurements on each person before and after an intervention is applied, and again, ideally that would be done in a control group and in an intervention group, but the context here is just kind of trying to detect a change or a difference within the matched pairs. So this would be kind of directly applicable to, you apply the intervention to everybody and then measure them before and after, and then look at the difference. So this is going to be similar kind of in operation to a one-sample test, where the null hypothesis would be that the mean difference within the pairs is equal to 0. So for means, this would be a paired t-test, which is identical to a one-sample t-test on the differences. This is, many of these tests are special cases of kind of more general statistical methods. So for the paired t-test, that's kind of a special case of linear mixed models, which are much more general in the sense that they can accommodate more than 2 measurements per individual. They can deal with missing data in a way that a paired t-test can't, and so on and so forth. If you're looking at matched pairs with proportions, then you would be going towards Mac-Niemar's test. And other paired designs, like I said, you can use linear mixed models to deal with essentially the issue here that you're trying to account for is the correlation within a pair or within a set. And it's important to account for this for many reasons, because either depending on the direction of the correlation or the sign of the correlation, is it positive or negative, you can either over or underestimate your sampling variability, which means you could be biasing your results either toward or away from the null if you don't properly account for this. And mixed models again are kind of a general statistical tool or method for correlated data, which again, these are kind of special cases of those methods. So some general rules of thumb. The 10 subjects per variable is kind of a commonly used one. And when we say variable or predictor or covariate, this really means per parameter in your regression model. So when there is a, if you have, for example, a categorical predictor with more than 2 levels, then you're going to need more than one parameter to describe the effect of that variable on your outcome. In general, if you have k levels, you're going to need k minus 1 parameters in your model. So that's an important thing to keep in mind when applying this rule of thumb. And if you're in the logistic regression setting, or to some extent the survival regression setting, you look at the number of events rather than the number of subjects. Some other things to think about: multiple comparisons is something that I think comes up a lot. And this is something that we really try to avoid at the design stage, because we want to ensure that we're not finding spurious associations. So for example, if you have 4 groups and you're comparing them all with respect to means, then every pairwise comparison is going to give you 6 different tests. So if you just kind of naively apply your statistical test there, you have a higher probability of a type 1 error rate than your stated alpha level. So a simple method to deal with this is to just divide your nominal alpha, or your stated alpha significance level, by the number of tests, and then use that value within each test. So for this setting, we would divide 0.05 by 6, because 6 is the number of tests we're doing, and we would assign statistical significance for each test if the p-value for that test was less than 0.0083. So you're kind of increasing the strictness of your statistical hypothesis test in order to counteract the fact that you're doing a lot of tests. And this can come up at the design stage by, you can adjust your sample size for a smaller alpha, for example, in this setting. And what it's going to do is it's going to require you to have a larger sample than you would have if you just did one test. So again, multiple comparisons is something that we try to avoid, but if it's unavoidable, we have to correct for it oftentimes. So this is why it's good to kind of plan in advance for all your primary and secondary comparisons, because what we want to avoid doing is mining the data. We don't want to be in the situation of kind of trying every test, throwing everything against the wall and seeing what sticks. Because it's oftentimes the case, I think, that this happens in research. If your primary outcome does not, or if your primary outcome is not showing significance, it's common practice to kind of look for sort of maybe reasons why that was the case, or to do numerous subgroup comparisons and things like that, which to some extent is fine. You just have to be aware of the limitations here. And the primary limitation is that you need to reduce your significance level for each test in order to avoid inflating your type 1 error rate, which is to say, if you did 20 tests, even under the null hypothesis, because your significance level is 0.05 or 1 out of 20, you would expect on average 1 out of 20 of those null tests to be significant. So this bond for anything is a way to correct for that. So a couple of things that we want to avoid in terms of sample size statements. One example, a previous study in this area recruited 150 subjects and found highly significant results with a p-value of 0.014, and therefore a similar sample size should be sufficient here. So this is erroneous, because that's just one study. So that's just one random draw from this population. And it's possible that study was lucky in finding this effect, because again, these are random variables we're dealing with. So it's possible that just by chance they got a small p-value. It doesn't reflect kind of the larger issue of power and sample size directly. So you can't use a p-value by itself to really make statements about a future study. That being said, I mentioned before that it's really helpful if, as I'm doing power calculations, if you as the researcher can provide me with, existing literature or your own pilot data, for example, which will, kind of help me determine the parameters that we use for the power and sample size formulas. So another kind of erroneous statement here would be the clinic sees around 50 patients a year, of whom 10% may refuse to take part in the study. Therefore, over the 2 years of the study, the sample size will be 90 patients. So the problem with this is that it's just basing sample size on number of patients that are available. And this could be much larger or much smaller than what you actually need for power. And so we talked about this being a problem in both directions, right? So if you have too many patients in your study, then it's at the very least a waste of resources, and at worst, you might be exposing patients to unnecessary risk, which is an ethical concern. And then at the other end of the spectrum, if you have too few patients, then the study could be, again, to be blunt, it could be kind of pointless because you're not going to be able to detect the effect that you're trying to detect. And then again, you may be exposing the patients to risk that's unnecessary because the study's not well designed. So what you want to do in this case is find you could start here as a sample size, but then find the detectable difference based on that sample size at 80% power, and then see if that's clinically meaningful or not. So some issues that may arise in sample size and power calculations are, if there's no prior information or no data, no literature in the area. So you wouldn't want to say, sample sizes are not provided because there's no prior information on which to base them. It's better to conduct a small pilot study, and of course, many times that's not possible. It's kind of this catch-22. You need the data to get the grant, but you need the grant to get the data. So this is where I can be helpful in terms of kind of helping interpret the existing literature, because you can often find similar studies. Maybe it's not the same population, but it's the same outcome, or maybe it's not the same outcome exactly, but it's the same treatment comparison. So there's a lot of ways to kind of, again, work backwards to the inputs that we need for the sample size and power calculations. And it's always going to be better than kind of throwing up your hands and saying, we didn't do any sample size calculations because we didn't have the data. So that's always going to be probably frowned on. I guess the one exception could be, if you are applying for a pilot study, you might be able to get away with this, but I think they would still want to see some kind of, again, you can usually at least give kind of a Cohen's d sort of effect size. But in other contexts, for example, where there's more inputs for the power calculations that you would need from preliminary data, that may not even be possible. For example, I mean, if you're doing something like a mediation analysis, then there's so many more inputs to that you're just going to have. If you don't have preliminary data, it can be really difficult to do that. So depending on the complexity of the analysis too, I think this is a little bit of a gray area. If there's specifically no information on the standard deviation of the outcome, then again, this is kind of what I was just talking about. You can use the Cohen's d, right? Because that's in units of standard deviations of the outcome. So another thing you can do, based on that is to make a table, assuming a different variety, a wide variety of possible standard deviations. And that'll be, again, a little bit, it's a linear function of Cohen's d. So on the one hand, it doesn't seem that helpful, but it does translate the Cohen's d into something that's probably more interpretable. For example, in the weight loss example, it's in units of pounds, right? And then it also helps you think through just kind of, holistically or heuristically, what's plausible as a standard deviation, because again, as clinicians, you guys have an idea probably oftentimes of how variable this outcome is. And so we can often get, based on these tables, you could say, oh, this side of the table, that's way too small. This is more variable than that. So that can help us kind of rule out some cases. So that can be helpful to do just in terms of kind of a thought exercise or helping you think through these things. And whenever in doubt, I think protecting yourself with a higher sample size if possible is a good idea. And again, the caveat is you don't want to go too large because you don't want to be wasting resources. But I think in the case where there's not sufficient prior data, then that can be a defensible strategy, because it's not wasting resources if you just don't have the information you need. And then you really want to be able to say, well, we did this study and it's conclusive because we had a large enough sample size to say that there is no difference of this size, for example. So some things about sample sizes to remember. I mentioned that it's all kind of to some extent guessing. It's an educated guess, but it is a guess, and it's an estimate. It's an estimated sample size. So it's not exact. It's not exact science. So we talked about how sample sizes that are too large or too small can be a waste of resources. You want to kind of balance the feasibility or practical side with the statistical or power side in terms of the design. And you want to think about your effect sizes as well. You want to choose your sample size so that statistical significance that you have power for would coincide with a clinically meaningful or clinically significant difference. And changes in the design could affect the sample size, as we mentioned, because design affects the methods we use to analyze the data, and the methods we use to analyze the data inform the power calculations. So with different designs, we can end up with different sample sizes. And the kind of this notion of attrition, right? The sample size is calculated for the number of people you actually will have data on. So if some fraction of those people who start the study drop out, then their data is not going to be fully available. So you'd want to account for that by using the dropout, the kind of post dropout numbers for your sample size calculations. So moving now into some questions of data, right? So we're designing a study, and we designed a study. Power is good, sample size is good, and we're collecting the data now. So a key point is to make sure that all the data that needs to be collected is collected, but that no data that's not needed is collected. So I would always err on the side of collecting more rather than less data, because this is not like the sample size question where you're wasted. Usually it's not a question so much of wasting resources. I mean, it can be dependent on the variables that you're collecting. But for example, if it's just extraction from EHR or something like that, then there's really no cost generally associated with extracting 10 variables versus 30, because it's just kind of some computer code that's different. In a primary data collection context, I guess it could be different, because if you're doing lab testing, things like that, you don't want to be doing that excessively if you don't have to. But a key, one of the elements here is you need to be sure you understand what each data element is going to be used for. Your primary outcome, that's the variable that represents or is represented by that is going to be used for your primary analysis. If there are other variables that you need to adjust for in the models, that would be a different use of data. So you want to think through and understand exactly what you're going to be using each of these data elements for. So another example, reducing the REST study, reducing end-of-life symptoms with touch. So the study design here was a randomized controlled trial of massage therapy versus non-moving touch among adults with advanced cancer. So the aim was to demonstrate the efficacy of massage therapy for decreasing pain, improving quality of life, and lessening physical and emotional symptom distress among cancer patients at the end of life. So right here, we see several potential outcome variables, right? So there's a pain variable, there's a quality of life variable, and there are physical and emotional distress variables. So one of the important things is to think about how each of these are measured. But what I would kind of say on the face of this is that each of these is probably measured by some sort of continuous scale. So we would typically be looking for a difference in means between the massage therapy randomized subjects and the non-moving touch subjects. So if our primary hypothesis is that massage will decrease pain among advanced cancer patients, then we need to think about, again, what's the test we're doing, right? So I mentioned that if the pain outcome is derived from these scales, then it would probably be a difference in means, but it could be a difference in proportions. If you say, you know, proportion of those experiencing severe pain or something like that. So, you know, it's important to think when you're collecting the data about, you know, kind of the way in which it's going to appear. You know, again, is it a scale? Are you going to use it as a continuous scale, and so on and so forth. And that kind of gets to questions of data formats. So, you know, this is just kind of a table showing the various aspects of data collection that's good to be aware of. So the form number here is kind of the assessment or the measure that's being used to measure pain, immediate pain versus delayed pain. So there's all sorts of ways to measure pain, you know, and many other things as well. And this table would show kind of how these things are being measured in sort of and getting into the weeds. And that's crucial when we're talking about data, is we really do need to get down to the nuts and bolts. Because it's all good and well to kind of describe your study in terms of general concepts, but when you're working on power and sample size, and then finally when you're collecting the data, you need to be very concrete about how these things are being measured, because it's often the case, I've found, that researchers say, you know, I want to measure distress or something, but then they don't know what kind of distress they're measuring. They don't know what to use to measure distress in terms of, you know, validated instruments and things like that. And this comes up less in some contexts than in others. If you're looking at things like psychological distress or pain or things that are more subjective, you need to think more about kind of what scales you're using than if you're measuring something like blood pressure, where it's, you know, kind of established what, you know, how that's measured, right? And then the variable name is kind of important for the analysis, less important for you as the clinician or the researcher. The visit number, this is where when the data is going to be collected. So for these measures, it's going to be collected on visits 1 through 6, but for these measures, it's only going to be collected on visits 1 through 4. So this is, you know, you'll often see or you'll often come up with in your grants kind of tables showing, you know, over time, for example, for a single patient, which visits are going to have which data collected, right? So again, it's very important to kind of be clear about that, because that's going to inform, you know, the analysis as well as the data collection itself. And then this last column here is just showing the range of the variables. So this is a scale that ranges from 0 to 10. And this column could also be, you know, we could have more columns here, and we could have things like variable type or something. And this would be, you know, it's probably an integer, but, you know, this is something that we analyze typically as a continuous variable most of the time, and look for differences in means. But you could have binary variables, you could have other kinds of variables. So, you know, another thing to think about is the form of the variable itself. So data structure, again, this is probably less important to you as the clinical researcher, more important to us on the data and analysis side. But it's, you know, I think it's always good to kind of consider what the data is going to look like, you know. So typically, you know, data is kind of this rectangular format where we have 1 row per observation and 1 column per variable. So if you're, you know, sharing data with us, then that's the form we would need it in. And, you know, a common thing that we see in data that's shared with us is Excel files with, kind of highlighting or, rows at the bottom saying mean, standard deviation, things like that, summary statistics. And, that is a little bit less helpful for us because when we do our analysis, we read these files in to a statistical analysis program such as SAS or R, and it's going to have trouble if there's, well, it's not going to really notice highlighting, but it's going to have trouble if there are, rows kind of containing means, because then it's going to think that's another observation, for example. So that's going to potentially cause some issues in analysis. So if you guys are in the position of sharing data with us, then ideally it's kind of just the raw data. So no manipulation, no highlighting, nothing like that. So kind of a common, not joke exactly, but a common thought among statisticians is that 80% of the data analysis time is cleaning and prepping the data for the actual analysis. And I think this is very true, and it's kind of an unfortunate fact because the data cleaning is not the fun part. The fun part is the analysis. But it's unfortunately the case that there's a vast amount of time that needs to be spent on preparing the data. And so that's just something to be aware of when you're working with an analyst or a statistician. There's going to be potentially a lot of time that needs to be spent on data preparation. So it can seem like, well, just to run this analysis, you should need to look at two means, right? You just need to compare two means. But to look at those two means, there's all sorts of stuff that has to go into preparing the data for that analysis that's kind of going on behind the scenes. So a data dictionary is another thing that's kind of crucial to come up with in consultation with your statistician. And this is going to be really helpful for everybody kind of throughout the study, but especially if anybody else uses the data later, if you share it as a secondary database. Or conversely, if you're using a secondary database, then you're really going to need this because it's the only way that you're going to know what's what in the data set, because oftentimes there's going to be variables that have names with a bunch of letters and a bunch of numbers, and you're not going to know what's what without this kind of code book. And this describes kind of the contents of the data, the way it was collected sometimes, the structure of the data, the format, so coding for various variables, is one female and two male, or et cetera, things like that. And then there's a link here for guides to data sharing, good practices for data sharing. So for analysis, we need to have numeric data. And I say numeric, and it doesn't have to be numeric when you give it to us, because we can always kind of convert things. But it is helpful if it's numeric. And this is where the code book comes in, right? So you could have numeric coding for a race variable where 1 is white, 2 is Native American, and this could go on and on. But you need that code book to know what's what. And there are definitely some kind of interesting situations where somehow this information is lost, and you have to figure out from context what's what. But that's never preferable. So you always want to if you're doing this coding yourself, you always want to keep track of what's being coded to what. And then free text fields are always to be avoided, because this is something we can't really analyze at all. I mean, it's fine if in your data set you have kind of a character variable for race that says white, that says Native American. We can still work with that. That's not a problem. And it's just kind of nowadays, I think this is probably less of a concern than many years ago, when there was actually so much typing. I think now with like RedCap and things like that, it's just a more streamlined process. So sorry, I'm just checking the time here. So we have 15 minutes, and I'm gonna do my best to get through the rest of the slides. But again, if people have questions, feel free to interrupt or let Ann know, and I can address them as we go. So data collection. If you're creating the variable names, be descriptive, but you don't want to have excessively long names. And this is something that your data analyst can help with, or a data manager or something like that. And if you have pre-post or data collected over time longitudinal data, it's important that we have a variable or a field to link people pre and post, right? Because if you just have pre and post data and no indicator of who was who, then that essentially becomes a two-sample t-test, where what you really want is a paired t-test, because that's going to be more efficient. So it's really crucial to account for the individual people in the study, and link them with some sort of like an ID variable, essentially. So, this is kind of an example of good or better ways to record data. So this kind of format down here is to be preferred because it shows that you want 1 decimal place for the weight and kind of 3 digits and no decimal places for the height. Because otherwise you can get things like, different people entering different levels of precision in your variables. I mean, some people could be rounding kilograms to the nearest 10, for example, or maybe not that coarse, but they could be rounding to the nearest single ones place. Whereas what you really want is you want that digit, that first digit after the decimal. So if you're collecting data, it's good to be kind of concrete about or granular about what you actually want in terms of digits and precision and things. So building your database, that's not something that I'm going to be directly responsible for. This is something you would need somebody on your team who has experience with database development. And some data analysts are able to do this, but I think oftentimes this is kind of a different role. But I think there's many people on campus who have this skill set. But it's data quality is kind of critical, because this is stuff that has effects downstream. If when we are analyzing the data or we're interpreting the results from the analysis, and there are outliers, which are values that are unexpectedly large or small, or in some other way kind of surprising values, you're going to have to go back to the database and try to find out what happened. So kind of it's good early on to be doing this sort of stuff while you're collecting the data. And this can include things like time of entry checks, where I think REDCap probably does this, and maybe other systems as well. But it won't accept a data entry value that doesn't make sense. So for example, if you enter a date of birth and a date of an event, and the date of the event is less than the date of birth, and you have a negative time to the event, and that doesn't make sense. So it's things like that, and you'd be surprised how often that kind of stuff happens, because we're only human, and when we're entering data or performing tasks like that, mistakes happen. But it's good to be addressing those kind of as they occur, rather than at the analysis phase later on. Then this, regular downloads will help with this. And it's good to kind of, if you have a multi-site study, it's good to have a notion of, who is going to be responsible for kind of interfacing with the sites about data collection. So there's a few options for data capture or recording. Excel, kind of, it's probably going to end up as an Excel spreadsheet, which is related to what we use for analysis. But Access, I don't know if people still use this. I think everybody's using REDCap now, which has a lot of advantages. It's a secure interface. It's web-based. I think it's easy to use. I haven't used it myself, but I think it's that's one of the appeals to it. There's different ways to enter the data. It has good facilities for data export, because I think it was designed by people with statistical training. You can export it in forms for SAS or SPSS or Stata or R, as well as just your standard Excel spreadsheets. It has good facilities for longitudinal data collection, and it also has facilities for randomization. And we didn't really talk too much about that, but if you need to stratify during your randomization, it can help you do that as well. So, in terms of the analysis and results, some of the things we need are a written analytic plan that can be developed, with us, kind of in consultation with us, but it's going to need input from you as well. And you can start from, the stats plan in the grant, concept and variable maps, things like that. It's one of the key things that I've kind of been emphasizing throughout is operationalizing your variables. So don't just say, measuring distress. You need to say this score is going to be how we measure distress. And, there's other examples too, like for age, which age is it? Is it the age at the beginning of the study, at the end of the study? And this obviously is more important in a longer term study. But it could have impacts on your analysis. So it's good to be concrete about that. Again, we talked about kind of timelines, manuscript ideas, prioritize lists of tasks. Mock tables are really important as well. So what you can expect from the analysis is results that are clear and interpretable. The statistician and the data analyst will help you write the methods and analysis sections of the paper, as well as the results. And we'll be able to provide charts and or graphs. Although I've worked with researchers who kind of prefer to do this themselves. So we're fine with providing data files that are needed to generate tables. So the rest of the talk is kind of a bit about sort of some troubleshooting things in terms of relationships with between the analyst or the statistician and the clinician. But I did want to give you guys kind of a dedicated opportunity to ask some questions. So I think I'll just hold off here, and then again, Anne will share the slides with you. So if you go through the rest of the slides and you have questions, of course, feel free to reach out, but I did want to kind of just pause here and see if there are questions.
I haven't seen any come through the chat, but please feel free to send them if you think of anything. I just have a few announcements, but if any questions come through, we'll certainly take those. So as usual, you will receive an email after this with an evaluation. If you'll please fill that out. And we will also include Dr. Rice's slides. Our next researcher training is Friday, November 13th from 8:30 to 9:30 a.m. It will be led by Dr. Janine Higgins on how to hire so you don't need to fire. We thought with the hiring freeze starting to lift that this might be an especially useful training for everybody. Dr. Higgins is a great leader on campus and has some really great lessons and perspectives on how to hire somebody and get the right person for what you need. And then finally, our annual community event, formerly known as our luncheon, is on November 11th from 12 to 1:30 p.m. Our keynote speaker is Dr. Lori Santos, a professor of psychology from Yale, who will be presenting on the science of well-being. So keep an eye out. You'll all be receiving an email from us on how to register for that. And it is, of course, virtual live stream. So we hope you can tune in from wherever you are. And I think I don't see any questions coming through. So thank you so much, Dr. Rice. It's so valuable to have you as a resource and an expert in this area. I know it's all over my head at least. So thank you very much.
Thank you. Yeah, I'm glad for the opportunity to take part in the trainings. Hopefully people got a lot out of it.
Yep. Have a great day, everybody, and a great weekend.
All right. Thanks, everybody.
Thank you.
Bye.
Bye.